once again, warm welcome to all of you. In today's segment, I shall try to explain about maximum power point of solar PV and how one can track this maximum power point using maximum power point tracking, that is MPPT algorithms. Let's begin the session. So as far as introductory part is concerned, the solar PV comprising of 4 points that we are considering in this case. These are open circuit voltage, short circuit current, maximum power point voltage and maximum power point current. Now this maximum power point voltage and maximum power point current shall vary with the change in climatic conditions, that is insolation and the temperature. So let's begin the discussion about these topics. So as far as brief outline is concerned, first of all we'll discuss about some prerequisites in very fast manner, that is what are the IV and PV curve of solar photovoltaics and its maximum power point on the curve. Then I'll try to focus on concept with this MPP point using buck-boost converter by incorporation with duty cycle, and I will try to explain the concept of MPPT with some simulation analysis using buck converter. Then I shall discuss about this maximum power point tracking algorithm. Particularly, I have tried to focus on incremental conductance and perturb and observe method. Our next segment is design of inductor and capacitor that is used in this power converter. Then various converter topologies, and if we can have various adaptive MPPT mechanism, and how one should incorporate this into the solar PV system. So as far as MPPT algorithm is concerned, we need to focus on maximum power point. So this is the graph of photovoltaics, that is IV curve of photovoltaics, in that with the change in radiation various maximum power points have been tracked. And this is what the range of V means. In the earlier sessions, what we tried to conclude is from the IV curve, usually the radiation and temperature both are vary simultaneously, but the short circuit current is mainly depending upon the radiation and the open circuit voltage is mainly depending upon the temperature. So our basic aim of this discussion is to track these points, and these are the maximum power points. If we can talk about of a particular radiation, we can also draw a PV curve, photovoltaic curve, that is PV curve of PV, that is power versus voltage. So in this case, if you can go with this PV curve, so in that case this is our maximum power point that we are going to track. Moving further, if we have particular data with us, so we can track this point. Now this point may vary if the radiation may decrease, it may increase due to some extent if the radiation will increase. So this is our basic prerequisite that one should know. So how we can have this maximum power point tracking algorithm? So in that case, we can see our discussion of the topic. So this is what the concept. Over here, a converter named as buck-boost converter that is the heart of the maximum power point tracker, has been highlighted in the rectangular dotted lines. We need to control this switch. Now if you can see that if the switch is closed at that time, the inductor will charge. As the inductor will charge at that time, the energy will not flow to the load because this diode is behaving as a reverse bias, but during switch will be off, the inductor energy will be released through the capacitor and the capacitor will provide the energy to the load. And this can be happen with very high switching frequency to avoid the interruption of the power at the load end. So this is what the concept of control, that is how we can control the switch. So in general, we are going to generate through algorithms a pulse train which can turn on and turn off the switch as per change in the climatic condition of the source, and accordingly the power flow would be reached at the generator, that is generation part over here, the PV generator, to the load, known as the maximum power point tracker. So if you can see that we are having the various options, that is when the switch is closed. So if you can close the switch, the inductor will receive the energy from the solar, PV or any source. So when the switch is open, at this case the inductor will discharge and the capacitor will also discharge through the load. So you get the uninterrupted power from source to load. Now if you want to operate the switch, we are going to introducing the duty cycle. If you are going to introducing the duty cycle, at that time it controls the relationship between the input and output voltages of the converter, and the variation in the fraction of the switch is in on state, or the other is deferred to as PWM. So there is on and off mechanism, and accordingly we are going to change the things. So at that time we will discuss about the same, how we can change the concept of introducing this duty cycle. So this is what the on off pulse train we are going to generate. So if you can talk about the same thing, if my duty cycle equals to 0.5, my converter is in the floating mode, we can say. If you can go with the buck and boost operation, for if D is greater than 0.5, this is what our duty cycle. If D is less than 0.5, this is what our pulse is in the same. So the duty cycle D is the fraction of the time for the switch is closed. So if you can go with this thing mathematically, not go into the detail because it is very easy to understood. We will check about the on time and off time. So our input power is 1 upon T integration 0 to dt, because this is our on time. So when the switch is closed, from time t equals to 0 to t equals to dt, and the voltage across inductor is at the constant voltage Vi for that time, so it will be continuously rising. So if Vi, that is constant, and IL, that is constantly rising current with this time. So under these assumptions, at a particular instant the current is constant, that we are going to assume. So the average power into the inductor is VL IL into D. So D, that is nothing but the duty cycle. So when the switch will be open, the inductor's magnetic field being collapsed, and it will return the energy just what we have acquired, and simultaneously the capacitor will charge, and capacitor will also discharge through the load. So during on time, when inductor will charge, during off time inductor will provide the energy. So at that time, during on time also, the load will get the power. During off time also, the load will get the power. So at that time, output power at the load end equals to 1 upon T integration dt to T VL IL. Again, VL is my output voltage. I'll keep it outside. IL, again, I'll keep it outside, essentially constant. So the average power is integration dt to T dt. So T minus dt. I'll put T common. It will get cancelled out. I'll get V0 IL 1 minus D. So in a complete cycle, it is a ratio of output voltage upon input voltage, that is equals to minus D 1 upon D. So equation 5 is very interesting. It tells us that how we can bump the DC voltage up, that is boost converter, or down, that is buck converter. So if there is a down sign, there may be a change in sign just by varying the duty cycle of the buck boost converter. If we are having a longer duty cycle, it will allow more time for the capacitor to charge and less time to discharge. If you have a shorter duty cycle, vice versa it will be happening. For duty cycle equals to 1 by 2, the output voltage is same as the input voltage. So duty cycle of 2 by 3 results in a doubling of the voltage, that is equals to D equals to 1 by 3, cuts the voltage into the half. So an actual MPPT tracker needs a some way of this DC to DC converter. It might be a boost converter, it might be a buck converter, it might be a bidirectional converter, it might be a buck boost converter, whatsoever topology that one can select. How we can introduce this duty cycle? So in this example 9.2, we shall check the duty cycle for MPPT. So under certain ambient condition, a PV module has its maximum power point at Vm equals to 17 volts and Im equals to 6 ampere. So at what duty cycle should this MPPT have if the module is delivering power to 10 ohm resistance? Now this example typifies the incorporation of the load in the system. So the maximum power point delivered, in this case this maximum power is P equals to V into I. So in this case V is given, I is given. If we multiply, we will get 102 watt. So if we are considering 10 ohm resistance that is acting as a DC load, so the load voltage will be P equals to V square by R. Over here the voltage required across the resistance that we need to find out, that is nothing but 31.9 volt. In this case the MPPT must bump this 17 volt into this much voltage. So again it works as a boost converter, and we are going to introduce the plus sign over here. So our original equation is V0 upon Vi, that is output voltage upon input voltage. Output is what we found, 31.9, divided by input voltage is 17, equals to D minus 1 upon D. If you can solve, you will get the 0.65, that is more than the 0.5. That's what we discussed in this case. So this is how the voltage will bump up if we are going to introduce the duty cycle. So if we can consider 100% efficient MPPT will produce the duty cycle in this manner in terms of voltage and current. Now this diagram explains lots of things. It's nothing but the DC transformation. So if you are going to increase the voltage, your current goes down. In similar way, if you are going for the buck converter, your voltage will go down, and in that case your current will be increased in the output of the converter. So the figure shows that the MPPT bumps the PV voltages and current to approximate values for the load, because in this case we have not considered the voltage regulation of the load. So we shall discuss further about the duty cycle. If you can draw this duty cycle graph. So these are the graph of IV curve of the PV by the incorporation of the duty cycle, keeping the radiation and temperature, that is climatic condition, constant. So over here, if my duty cycle is D equals to 1 by 3, that is 33%. So at that time I have a double of ISC and VOC is half. It works in the buck mode. This is our original IV curve. And if we can talk about the same thing, if I can double the voltage, my current will be half. So this is what the modification of IV in PV curve. So if we will connect the load using buck converter, then how it is look like, that we shall cover in the next session. Thank you very much for your patience listening. Our learning outcome of today's class is how the duty cycle will change the voltage and how your power will remain constant. Thank you very much for your patience listening. Thank you.